think so. Well, welcome to the final and concluding session of the ITC Pizza Lunch series that we've been having on gravitational wave astrophysics. It's lovely to see the turnout. So let me give you a little bit of background. The original vision with the entire series was to provide a sort of mini course on the subject. Now, the field has had something of a stepwise function of interest in light of the LIGO detection, right? There was a little bit of precursor activity with that subspace chatter on Twitter, right? But then it kind of ramped up with the successful detection. And so it was timely to have a kind of crash course for the entire community to understand the various frequency ranges and sciences that can be covered in this burgeoning field. So with co-organizer John Forbes, we went to task and tried to find the best people that we could find both locally and outside the CFA to discuss the various components of gravitational wave astrophysics. We originally set out to do it in a linear story, but given people's schedules and a minimal budget, that was impossible. But thanks to the internet and hypertext, now you can now revisit these talks in any order that you choose to. And I hope you will. And that's a service that we've tried to provide, is that you can go back to the web page and watch the talks, and the slides themselves will be made available for those who are interested. Let me just go through here. So why are we here today? Right? So normally at the end of a series, that's it. The last talk, we go about our day, our week, our schedule. But wanted to do something different, because you walk and there's minimal memory retention of what was had in a talk, right? Maybe you scribbled some notes down, maybe you had a conversation, but then it's gone. So I wanted to revisit the entire series. And that's what we're doing here in what we're calling a flipped session. So instead of a talk that takes up most of the time with a minimal discussion, we're having a minimal talk followed by a lengthy discussion. And we've invited some panelists to help guide the discussion in certain directions, but it should be driven by you, the audience members, about what was learned and where we think future directions are most exciting. And speaking about being brief, I want to also mention, so in light, to make this conducive, the entire room has been wired. So normally it's just the person with the rock star microphone or this, but we have the short mics put on so that all conversations can be heard. Okay? So try to minimize ruffling about as you can, okay? And gossip will be picked up as well, so keep that in mind as well. Okay, so before I pass on to John and Rosanne, I also want to mention cake. We started off with a cake, and we have another cake. It's very difficult to see, but just like similar to how difficult it is to detect gravitational waves, it's difficult to detect what's written here. So it's GWA, and then this was supposed to be like the LIGO wave detection, okay, and ITC at the bottom. So we will share with this and pizza in the ITC lounge following the discussion we have here today. So John, please go ahead, and he's going to talk about just a summary of the topics that we're covering.
Yeah, exactly. So this is just supposed to be a very broad overview. I just can't do justice to the 12 hours of talks that have occurred, but I wanted to sort of warm everyone up and then turn it over to the panelists. So first up, this is sort of the broad landscape of gravitational waves, and it's what we had in mind when we were designing this series. So on the top you have various sources which we think will emit gravitational waves, and on the bottom we have the detectors which we think will be able to see them, and the frequency of all these things. And so, like I said, in designing this series, we tried to sort of cover the whole spectrum, but of course we ended up with a few more at the high frequency end where there's actually been a detection. So one of the key things in this is the detectors and what their capabilities will be, and lots of people included various timelines in various flavors on their slides. So I thought I would put that all together into one unified timeline here to remind everyone and to sort of let everyone compare where all these things will be simultaneously with each other. So on the top here we have the year in 2-year increments, And each row is different sort of detector technology, so CMB, LIGO, pulsar timing arrays, LISA, and electromagnetic follow-up. And so at the top we have CMB, which we've heard is steadily progressing in sensitivity. In fact, there's sort of a Moore's law in sensitivity to R, the tensor to scalar ratio. And you can see that that's happening very rapidly. LIGO is also ramping up very rapidly, so they're increasing the volume to which they're sensitive quite steadily, and adding new detectors, and maybe in the sort of 5-year time span, they're really going to be having major upgrades to the capabilities on the ground. Pulsar timing arrays, the numbers here are the probabilities of detection from Luke's paper, from Luke's talk. And you can see, within 10 years probably there will be a detection of the background from PTAs. One of these things is really not like the others, and that's LISA. The soonest it will be launched is 2029. So that's good to keep in mind, and actually the nominal launch date is even later. So, and then of course many of us are astronomers here, so we're familiar with these electromagnetic things that will be coming online and allowing us to follow up and understand these sources better.
What's XRS?
X-ray surveillance.
Links.
Okay.
This is pretty close.
Yes, I took this from Edo's. Okay, so these are the detectors and what they'll be able to do soon. The sources divide up pretty nicely into binaries and everything else. So binaries, we have neutron stars, black holes, and supermassive black holes, and the various formation channels. And I'll say another word about that in a second. And then the other things which we haven't detected, various things from the early universe, which there are a huge number of flavors of these models. And there are also a large number of sort of supernova models that may give you gravitational waves at various strengths. So these are sort of areas where theory has been allowed to run wild, and a detection here would be sort of really revolutionary in either of these areas. And just to remind you, sort of the key thing determining the emission is just this order of magnitude estimate for the strength of the gravitational wave strain, and it's v squared over c squared times the Newtonian potential. Just to remind you. Okay, so let me say one word about binaries. So what can we learn about binaries? What can we learn about these sources in terms of astrophysics? So, so for the stellar mass binaries, the real question is how do you form these binaries? And there are a few stories. One is just evolution of isolated binaries in the field. Another is formation in globular clusters dynamically, and there are other dynamical formation channels like the one Imre Bartos told us about, which involves black holes in a cluster around a supermassive black hole being captured by an AGN disk. And this has interesting consequences for the ability to follow up and understand these sources. And for supermassive binaries, it's basically the same question: how do you get these things close enough that they'll actually merge? That's the classic final parsec problem. And we would learn about all these things by understanding these gravitational wave sources. The other physics we can learn about falls into these categories. So again, supernova, there are many different models. We don't understand the core process in these supernova very well. So detecting one in gravitational waves would give us a very interesting window into that. From the early universe, we're getting to the point with the new detectors in just a few years where we'll be able to rule out vast sets of parameter space, including some of the most natural models of the early universe. There are also tests of general relativity, so the No-Hara theorem has predictions for what the signature of the gravitational waveform will look like after merger. And so if you can get a good signal of that, you can test this theorem. And another big topic was the complementarity of electromagnetic observations. So this sort of divides into two categories, follow-up and detection of candidates, searching for candidates. So we heard from Edo that follow-up is extremely difficult right now with the huge error circles. That will get substantially better, but will still be challenging. But of course, if you can actually detect a counterpart, you can learn a great deal about the source. And in terms of candidates, Luke told us, and Dan also told us about the surveys to search for monitoring AGN and searching for periodic variability. And there are a large number of candidates there that may interface with what we'll see with pulsar timing arrays and low frequency gravitational waves. So let me stop there. And so this is just the summary of the summary. So I think things are moving very fast on the ground, at least. There's a nice division of the sources and a nice division of what you can do with electromagnetic observations. So with that, I think I'll hand it over to Rosanne to start the panel discussion.
Oh, thank you. Yeah, we should probably all go over
Yeah,
to
please.
the table. Okay, well, this is the main part of the event, and we hope that you all will participate both by asking questions and saying anything that you think would be relevant. We stand at a very unique time in the field in that we now have 3 detections, and probably a year from now, with all of the promises that have been discussed at various points in this series, a year from now we'll know more. And certainly in a few years we'll know more about the rate and also the types of events and the expected versus the unexpected. With regard to the unexpected, one of the main challenges we face is recognizing signals that may never have been predicted in these very complex data sets. And that's a challenge that I think affects all of us who are interested in the field. We can make predictions of things that would be very difficult to detect. How will we help the people who are looking for signals to find the signatures? And before we move to the general discussion, there's one theme that runs through the various notes that they've sent, and I think what John said, which is the fundamental versus the fundamental. And by this I mean that as astronomers and astrophysicists, we have certain scientific questions that are fundamental to us, that have to do with understanding black holes in the context of AGN or understanding binaries. And we know they're interesting, we know why they're interesting, and they motivate our lives to some extent. But there's also fundamental in another sense, and I'll give as an example studying velocities in galaxies, which led to the discovery of dark matter, or studying type 1a supernovae, for which there were very many fundamental reasons to look for it, that led to the discovery of dark energy. So here we are, not only in a new field, but in a new way of detecting the universe, a new window to the universe. I think we all hope that there will be many truly fundamental discoveries that will appear so to people across fields, whether they're terribly interested in astronomy and astrophysics or not. And what those things will be, whether it will be understanding strong gravity, quantum gravity, unification of forces. We don't really know yet, and that's one of the things that I think we'll all keep in mind. Now, we were very lucky to get 4 wonderful panelists here, and the pattern will be that I will call on each one to give a 1 to 2 minute discussion of what they're interested in and what they think the important questions are for the future. And then we're going to just open it up for questions, and that will be the main part of this event. So I'll introduce the panelists as we go along, and I'm going to start with Cora because she is the person who has a slide here. Actually, it's right up here. Thank you, John. So Cora Dvorkin, she's our own Cora Dvorkin. She started here just a couple of years ago as a postdoctoral fellow in the ITC and quickly made very important contributions to the study of the cosmic microwave background. She's now an assistant professor in the physics department doing some very interesting work, and we're pleased to have her here today. Thank you. Cora?
Yeah, so let's see. So I am interested in gravitational waves, but the primordial gravitational waves, the ones that are coming from the very early universe. And the key, I have been asked to summarize the key outstanding questions from the community for when looking at trying to detect these primordial gravitational waves. So the fundamental physics that we are trying to understand is basically whether or not there is a new scale for particle physics. We could have a window into grand unified theory type of energy scale, so whether or not this can be measured, what can we learn about it. Then there is also the fact that if we were able to measure primordial gravitational waves, this would be a smoking gun for inflation. Of course, it would not be a proof of inflation because this is not a direct proof, but it's strong evidence for a period such as inflation happening. And then there are other questions related to how far did a field in the early universe travel. The tensor to scalar ratio would give us an idea of whether the field moved in a super-Planckian distance or a sub-Planckian distance in field space. And the prospects for the future are basically now, so the CMB community divides the different experiments in stages, and the different stages basically increase by order of magnitude in the number of detectors built, and therefore the sensitivity that we can reach. So now we can say that we are at stage 3. We're talking about 10 to the 3 order detectors, number of detectors. There are many experiments that are currently underway trying to get a sigma of R of about 10 to the minus 2. And I am part of this very vast effort of the CMB community in trying to propose the CMB stage 4 experiment. I'm sure you heard about it. We wrote a science book. This has been proposed to the different funding agencies, and the CMB stage 4 experiment would be able in principle to reach sigma R of 10 to the minus 3. This would rule out a vast number of inflationary models, but really, I mean, this is not the key thing to take, in my opinion, from this, because you can always build inflationary models given the restrictions coming from the data. Really, this will be able to tell us something about the energy scale that happened or didn't happen in the early universe. And so CMB stage 4, again, is a proposed experiment. It's planned for the next 10 to 20 years. And the key factors in both CMB stage 3 and stage 4 experiments are basically dealing with de-lensing, which is a way of subtracting the gravitational lensing that acts now as a noise in the B modes, and also trying to understand the complexities of galactic foregrounds, which are the main remaining issue in this whole business of going after primordial B modes.
Well, thank you. Thank you very much. I know you probably have some questions now, but let's hold them in our minds for a little while until we move through the other panelists. I'd like to next introduce Dan. Dan DeRazio joined us this year in the ITC from Columbia University, and he's been doing some very beautiful work in terms of studying various signatures that come from binary black hole systems. You've heard him speak here at this in this seminar series. So Dan, would you like to summarize for us the prospects for the future and important questions?
Sure. So I've spent a lot of time thinking about and have been very interested in what types of electromagnetic signatures teach us about gravitational wave sources. So not only counterparts to a gravitational wave source, something you see at the same time, but also just unique identifiers of something that will create gravitational waves in the future or has in the past. And using that as to supplement information you get from the gravitational wave sector. So the talk I gave this semester was related to massive black hole binaries at the centers of galaxies. And these are sources of low frequency gravitational wave radiation, as John already mentioned. And what I think is so fascinating about these is that the buildup of massive black hole binaries through galactic mergers really sets what we see in the large scale structure of the universe, and it has a lot to do with galaxy evolution. And there is this mutual interaction feedback between the growth of massive black holes and their galaxies. So something I've been most interested in is how can we find these unique electromagnetic identifiers of binaries throughout their lifetime, from galactic merger down to gravitational wave merger. And right now, we don't even know for sure whether or not massive black hole binaries merge. There's no concrete evidence of massive black hole binaries at the close separations or gravitational radiation is driving them together. So one of the questions that really drives me now is what will it take to really be sure from the electromagnetic sector alone that we're seeing a massive black hole binary at the center of a galaxy? And then from there, I think we can learn a lot about the processes that bring them together. If we can characterize the population of these binaries at different times in their life, then we can start to learn what are the environments at the center of the galaxies that bring them together. And then even beyond that, when you have something like a LISA signal, a thin sparkle of massive black hole binary with, say, electromagnetic counterpart to this, then you can start to ask not only tests of gravity, but learn about accretion physics. You can see from gravitational waves what the gravitational potential is doing, and from electromagnetic waves what presumably gas and zinc binary is doing. You can learn a little bit about accretion as well as gravity. So I guess the discussion points I'm interested in is what can we do to convince ourselves from electromagnetic observations that we're seeing massive black hole binaries at the centers of the galaxy.
Thank you. Of course, that then motivates Lisa, right?
Lisa,
What
and also,
motivations of Lisa
I didn't mention
also-
anything about the pulsar timing arrays, but putting these electromagnetic tracers with gravitational wave background would be one of the great consistency checks to learn about that population.
Does that mean we should move on to Luke? So Luke is here, and he has done, as you know from his talk, some important work in terms of pulsar timing arrays, and he has agreed to tell us a little bit about that.
Sure. Yeah, so I'm working on a very similar array of objects that Dan is working on, so also the supermassive black hole binaries. And I've been looking more at kind of the gravitational wave side per se. So how these could be observed in their gravitational wave signatures, which is namely by pulsar timing arrays. So you use precision pulses of pulsars to measure the local space-time. And in that case, you're sensitive to kind of more massive black holes, 10 to the 9 solar masses, 10 to the 10 solar masses or so. And models kind of seem to be converging that we can expect a detection within 10 years or so. There are even some signs in the data that the noise levels aren't going down quite as fast as possible, and some people are more excited about that than others. But this is an incredibly kind of uncertain regime of dynamics where, as Dan said, we haven't really observed any supermassive black hole binary, so it's very hard to constrain these systems. And a priori, there's no reason to insist that they coalesce at all. So this is a very kind of open regime to understand the physical processes that are occurring. So once we detect a gravitational wave background in particular, using pulsar timing arrays, it should tell us a lot, not only about the massive black hole population, so what the mass function of massive black holes are, what their merger rates are, but it'll also tell us about the environments that they're coming together in, so the stellar environments, the stellar scattering that helps harden them together, the gas accretion, viscous disk that also helps bring them together, their centricity distribution, so there are a wide array of properties that this will really be measuring. I think it's a really exciting frontier that's understudied. And then, of course, that connects into possible LISA sources, which would be the lower mass counterparts, so 10 to the 5 to 10 to the 7 solar masses or so, maybe even getting down into the intermediate mass ratio regime. So I think there's a lot of exciting stuff happening here, and it should be getting a lot of attention in the coming decade or so.
Thank you. Okay, well, I think you know Edo, and from his talk, which I know many of you were at, he gave a wonderful overview of what some of the open questions are for astronomers who would like to understand the electromagnetic signatures. So Edo, what do you think the most important issues are?
Yeah, so there are a couple of things I wanted to bring up. One is something that I think will happen, and I'll talk about in a second. And the other one is something that's been bothering me for the last few weeks and has been on my mind, so I'll share it with you. So the first one is the detections of electromagnetic counterparts to binaries that contain a neutron star, or at least that contain a neutron star that will be disrupted by another object. So neutron star, neutron star, neutron star, black hole. As I mentioned, there are multiple potential electromagnetic signatures of that, some of which are isotropic and should be in principle detectable for every event, some of which are non-isotropic and might be detectable for a small fraction of events. But I think it is almost inevitable that at some point in the next 2 to 5 years, we will make electromagnetic detections of neutron star binary mergers. Advanced LIGO is getting to the stage where the detection rate for neutron star binaries is expected to be at a level of about a few events per year, maybe one per month. And there is quite a concerted global effort using a wide range of telescopes to look for electromagnetic signatures, and we have some ideas of what we're going after. So I think that will happen at some point in the next few years. The thing that's been bothering me is it's clear now, even after the first observing round of LIGO, that the event rate will always be dominated by black hole binaries. And if you remember the talk from Matt Evans talking about the next generation, so just going from first generation detectors to next generation, essentially we'll see all the black hole binary mergers in the universe, right, which I think is quite astounding. And he was talking about rates of a few detections per hour. Black hole binaries coming from out, potentially beyond redshift 10. So the thing that's been bothering me, the question on my mind is, what are we actually going to learn? How much information can we squeeze out of these sources, given that we don't expect them to have electromagnetic counterparts, that they will not be uniquely localized to galaxies or to specific stellar populations? And really, the numbers we'll have to work with will come directly from the gravitational wave data. The masses, maybe something about the spins, the event rates, and a redshift distribution. Are we really going to be able to piece together a picture of how these systems form just based on that information? Whereas in the case of the neutron star binaries, we can hope to localize them precisely, understand a lot more about the physics and the formation of these systems. So that's kind of the open question that's been circling in my mind for the last few weeks, and I don't have an answer.
That's a very good question and a very good discussion point. So I think this really is the time to bring all of you in. Who'd like to start off? James, thank you.
I'll directly address Edo's point first, since it was the last thing we talked about. But I'm just curious, like for black hole mergers, in principle, you can get perfection for the prediction of the gravitational wave signals from GR simulations. With neutron star, black hole, or neutron star, it's going to be extremely difficult to cover the entire parameter space in a reasonable way where you can get perfect gravitational waveforms for every single possibility. So I wonder if one way of discriminating which ones do you want to follow up, whether they're black holes or whether they're neutron stars, could be determined simply by seeing how good of a waveform you have that comes out of the gravitational wave detectors.
Well, so I'm not an expert on the gravitational wave detection itself or the templates, but I think you can generate excellent templates for black hole binary mergers, but there's also what you measure, and what you measure has degeneracies, right? And so, for example, you can generate templates for a variety of spin orientations of the individual black holes and relative to each other into the orbit, but what you measure has degeneracies, and spins, for example, are not as well measured as masses. And even when you measure spins, you're not measuring the three-dimensional, you're measuring some projection of the spin. So again, in my mind, there's a finite amount of information you can squeeze out of the gravitational wave data, which is astounding in and of itself, but it's not a complete set of parameters for these binaries. The question is, with those numbers, can you really make progress in understanding the formation of these systems? For the neutron star binaries, you presumably will have some added insight from the electromagnetic signatures that might feed back into understanding how the system formed and maybe breaking some degeneracies about the gravitational wave signal itself, like the orientation of the binaries or something.
John touched on Carl Rodriguez's slides. He was talking about how you can use the mass distribution, the eccentricity distribution, the spin distribution, all as kind of probes of the underlying population. So how optimistic are you that those will actually be sensitive probes? Will it kind of just be a statement on dynamical formation versus field formation, or can we get more out of it than that?
So I thought that was an interesting talk. The part that wasn't clear to me is, of course, when you start with population synthesis models, whatever ingredients you put in, you can test one particular. My suspicion is that the astrophysical population of black hole binaries will be a mixture of dynamically formed systems and primordial systems, field systems. That fraction might change with environment, it might change with redshift, and what we will have is some agglomerated version of all of that. So I'm not so convinced that, maybe if it was really purely one channel versus the other, you could tell the difference, but I'm not convinced yet.
I'd just like to inject a note that I think the population synthesis calculations are extremely difficult, and at this point, Cora made an interesting statement that you can always make a model of inflation that will be consistent with your observational signature. If that's true for inflation, it's true even more so perhaps for population synthesis. So let's take some questions from the audience now. Yes?
So regarding Edo's statement about a lack of EM counterparts, I think it's a bit too early to rule this out completely. I wanted to highlight a recent paper by Barry McKernan and Savick Ford from the American Museum of Natural History, where they show that electromagnetic gravitational waves should excite pulsations in stars when they pass through those stars, leading to, you can think of this as a luminosity wave traveling through the stellar population of the galaxy. Now, if this is true, and if you could detect such a wave, you might be able to better localize the sources of these gravitational waves. So I think we're going to see a rash of interesting theoretical papers that predict novel ways of actually seeing this in EM radiation.
Sure, I think we've already seen that as a response to the claimed gamma ray detection of the first LIGO source, right? And I think, so what I will say from an observational point of view, I think it's too early to try to address that question right now. The localizations are too poor. I can imagine that if we're in a situation 5-10 years from now where we can have, let's say, 10 square degree localizations for black hole binaries, especially loud signals where you know that they're nearby, we can actually place interesting limits on EM counterparts, which we cannot do right now. So all of the observations we've done so far cover maybe 10-20% of the localization region. You can't really say much from that. So that's what I was on the observational side. On the, I will still proceed under the assumption that most of what I've seen so far being proposed as EM signatures for black hole binaries, and in some cases also for neutron star black hole binaries, where the neutron star is not disrupted. The energy scale is fairly low in all these things, and they will be extremely difficult to detect. So I think the numbers we need to keep in mind for these things is they need to generate over 10 to the 50 ergs in some sort of a mildly relativistic outflow to be bright enough to be detectable across the EM spectrum. But time will tell. But again, I suspect that they're not going to be followed up by bright electromagnetic counterparts at all redshift that are going to be detectable at all redshifts.
I mean, one exception might be if you have a black hole merger in a model that actually, the black hole has just been formed. And so if you still have the contents of the star that black hole was made by very nearby, you may see something much more like a kind of a supernova signal, which would be interesting. But you're right that in the canonical model, you don't.
Or even AGN disk, somebody wrote paper on this.
If we really think that that's the primary formation channel, then that's fine.
Are you a co-author?
No.
Otherwise, we'd be having a different discussion.
Is it possible in the case of an AGN disk you don't create enough luminosity to see, but you can affect the waveform? Probably not, now that I say it out loud. But I mean, I was just putting it, can you look for changes in the waveform that are due to the environment rather than electromagnetic signal from the environment? Maybe more in the Lisa band than in the LIGO band. So.
Ramesh, you had a question.
Actually, for Cora. So, this lensing noise, right? So, you want to eliminate that.
Yes.
So, what are the ideas that the community has on that? Can we measure it independently and subtract it out?
Yes.
How would you do that?
So the idea is you can statistically reconstruct the gravitational potential by using, so there are different kinds of ideas. First, you could do it internally to the CMB. So you could use different multiple moments correlations of the temperature and the E-mode field. And in order to reconstruct the gravitational potential. So once you have reconstructed the gravitational potential, you can have a reconstruction of your lensing B mode and subtract it up to a certain level. You cannot subtract it, even with the perfect experiment, there is no 0% residual. You will end up with some residual coming from the statistical nature of this reconstruction. And then another way of doing it is, for example, cross-correlating using the CIB or some other tracer of the gravitational potential. Because you need something that traces the gravitational potential and that has sort of a kernel at redshift of about 2, which is when the gravitational lensing has its kernel. So the CIB could be another way of doing this.
But what about directly using weak lensing?
Weak
Of
lensing.
very distant galaxies or proto-galaxies? Like just observing it with optical telescopes or whatever. Because you know the field of interest, right? Let's say that it's going to be a bicep field. Can one actually do a real deep weak lensing survey of not the CMB, but of other background sources? Use them to actually measure the potential. And then, of course, there will be some redshift correction you have to make when you apply it to the CMB. But in principle, couldn't we do that?
To reconstruct the potential, you mean, right?
Yeah.
I think in principle that's a good idea.
Is anybody thinking of doing this?
So there are some papers, I think by Wayne Hu and Didier, pointing out something along these lines. At the moment, it's very, very noisy. So I don't think it's at the level of the CMB, which is very pristine. But in principle, it could work.
Would LSST do this, or would you need something more than LSST?
I was just going to
Just
suggest
to go
that.
deep.
That's the perfect, source, because it's going over it every 4 days.
Right,
Yeah.
and that's part of their main
Yeah.
motivation was to do these weak lensing
Right.
surveys.
The problem with lensing, I agree with you that it's a good idea and it's another way of doing it. The problem is that it also has its own systematics in the PSF, and I'm not sure it's a good question for a survey like LSST, how well you could do, taking into account, this whole new arena of systematics.
Yeah. To me, it seems a statistical approach is always going to be less powerful than a direct measurement. If I know exactly what the potential is doing, I can subtract the true potential of this field rather than having some model of what its statistical properties must be and using that to subtract. So yeah, cross-correlation with other observables is a good way, but then there'll be all these bias questions and
That's true.
how well does the infrared actually follow the real potential,
Right.
stuff like that.
Right.
Lensing is the one thing that directly sees the mass and the potential, as Rosanne well knows.
Well, I was going to say, this is some nice work for you. I think you've
I'm just,
for the
but
next
it seems to
few
me
years.
the
I mean,
obvious
it's
thing that somebody should have already done.
It's still an integral over the line of sight, so
Yeah.
you would not get exactly the potential at its place. You have to decompose it from.
It is an integral. So if you have, let us say, a source at redshift 5, you will get one particular weighted integral of
Exactly.
this line of sight, and then you have to translate it to the CMB at redshift 1000.
Yes.
There will be some weighting function, yeah. So there will be a little bit there.
It's not directly.
It's not direct, but
100%,
redshift
but
5 is almost 1000, I think, for in this business. So
So there's also a W first.
yeah,
It's supposed to do lensing for that.
right,
That's right,
yeah.
yeah.
And Euclid and who knows.
They're all
Yeah.
the things that are on the bottom of your slide. There was a question back there I want to make sure we.
Are you talking about the neutron star merger you might detect once upon that frequency? But the neutron star merger is the gravitational signal will be like a several order magnitudes weaker than the current, the first detection, right? So how far, the first question is how far can you expect to see it? I mean, how far? The second is what is the time delay between the EM, between gravitational signal and the EM signal, and the strong side?
Yeah, so when LIGO reaches its design sensitivity, which will be presumably 2-3 years from now, the average detection distance for a neutron star binary will be about 200 megaparsecs. Where they are now, so the way they quote their sensitivity now is to what distance would they detect a neutron star binary. So right now they're at about 80 to 100 megaparsecs. Okay, so we're talking about 200 megaparsecs, which means 10 times the volume and therefore 10 times the event rate. In terms of the delay, it depends on the EM signal and what waveband you're looking. So, for example, if you have a gamma ray burst be a counterpart, then the signal will be detected essentially simultaneous with a gravitational wave signal. If you're looking, for example, for a radio counterpart, it might be delayed by weeks and even months compared to the gravitational wave detection, just because of the specific physics of how you form the EM counterpart in different wavelength regimes. So it very much depends. I think in the optical we expect that the delay will be quite short, maybe of order a day or something like that. So it depends on the technique you're using and what wavelength.
So to maybe make Edo more sleepless. So also in connection with Rosanne's comment that we want to have surprises. So one possibility, I think, it's possible that the neutron star binary, the neutron star may actually be quark star, bulk, strange stars. It's a possibility, right? In that case, you might even not have an electromagnetic counterpart. Neutron star binary. I'm sorry about that. Okay, but in that case, your worry will increase. So, but I guess the question then is, is that ruled out by the GRB, short GRB connection? You had this work, short GRB, it's a neutron star binary merger. If you allow the neutron star to actually quark star, strongly bound, never been disrupted. Is that so? That maybe I don't have to worry about quark star because I hope there's some surprises because I hope the black hole is primordial black hole. That would be very nice. Otherwise, we're talking about it. Otherwise, it's just boring binary evolution.
No, that's just the other fundamental.
Yeah, so can you how confident you can rule out this, you have to have the neutrons break up, because of GRB connection?
Yeah, I think with the connection with short GRBs, I think that there's a lot of circumstantial evidence that connects them to neutron star binary mergers, but we don't have that very unique signature, right, which you would get from gravitational waves. So, as much as I would love to say that, that rules it out, I don't think we're there yet.
I guess the relevant question is, if it's a quark star binary, I presume it can still get disrupted, right, in the process of coming together. And if you disrupt a quark star, what will the quarks do? I presume they'll still form baryons, and maybe they'll make hard process elements.
Yeah,
maybe it won't be all that different. But somebody should compute this.
You can start with the hoop conjecture. Can you fit two within a short radius or not?
Yeah, right. I don't think they're that compact.
Yeah, probably not.
Not that
Well,
not that
it depends on what mass you're talking about, because their mass radius relation is completely opposite to neutron stars.
Actually, you might want to repeat that so I'm not sure if people in the back could hear what you said. I thought it was quite interesting.
Just the hoop conjecture, if you can fit as much mass energy inside of a short field radius as you need to make a black hole, then you have a black hole. So do they hit and collide and stuff come out, or when they hit and collide, are they already hidden behind a horizon?
Right. And that depends on the radius to mass ratio of the individual objects, then they collide.
Okay, yes.
Okay, going back to the CMD B mode, isn't it that lensing B modes have a very different multipole range compared to the primordial B modes, and that there's no real confusion between the two, or is that, do I understand that correct?
No. So there is overlap. You're right that the lensing B mode peaks at smaller scales.
Right.
But the gravitational wave B modes have, the overlap always depends on the amplitude of the primordial B modes, right? But you expect to have two bumps in the primordial B mode spectrum, one at the epoch of reionization when the photons were scattering off free electrons during reionization. The other bump at smaller scales happen at recombination. That's the target, for example, for CMB stage 4. And depending on the level of, and then the lensing spectrum peaks at even smaller scales. But at some point, these two spectra will cross. And it's, it depends on the amplitude, but for R of about already order 10 to the minus 2, so for current experiments, it's already an issue. So the overlapping scales, that's the answer.
Okay. So another question on the CMB is, you mentioned that the number of detectors that you have is going up dramatically, right?
Yes.
Okay. So I had the impression that that is not where the limitation is. It's more in understanding astrophysical foregrounds and this lensing and stuff like that. And that is where the limitation is, and that's not going to scale with technology.
Well, they go hand in hand. When you make more detectors, you increase the level of sensitivity. So now we are at the stage in which lensing is being an issue. Before it was not the issue. Before the issue was the sensitivity. And the foregrounds are, they're always there, and we don't understand them, so that's an issue per se.
So this projection of 10 to the minus 3 in R, I mean,
that is with yes, that's a good question. So that is with a certain level of delensing, which assuming this kind of assuming assuming using another experiment that exceeds, for example, SPT pole or ACT pole, you could use them to delens. But in terms of foregrounds, these are assuming some model that is very simplistic for the foreground. So that is a good point. These numbers may be very optimistic. we still don't know exactly. Foregrounds are very complex.
So maybe just rephrase the question, the same question.
Yeah.
I mean, for 10 to the minus 2, 10 to the minus 3, it's very aggressive. It seems to be very, given that currently we are already worrying about foreground, it's a big issue at stage 2, 3. Should that be optimistic, even when you reach 10 to the minus 3?
Well, we are worrying about foregrounds, but it's not that we cannot do anything about them. So we need to understand them, and they carry their own uncertainties. You're right. This is assuming a simplistic foreground separation algorithm, and assuming, that foregrounds behave with simple power laws, which may not be the case at all. But the idea is to do foreground component separation. That's what most experiments are doing, trying to understand them and taking them into account, and the correlation that the different foreground parameters have with the fundamental physics parameters.
So, I have a question for Emily. So we haven't talked much about the black hole, the supermassive black hole binary mergers, and so one thing I'm wondering is a point that came up about EM signatures of systems that are about to merge or in the process of merging that might feed into our understanding of event rates for LISA or the expected signal for PPA. But the part that's not clear to me, and I keep hearing kind of conflicting evidence, whether any of these light curves of AGN that people make that seem to show periodicities are really indicative of binary black holes or not. And I know that there are some people in the room who know about this and have been thinking about this. So I'm kind of wondering, what's the current state? Is any of this robust at all, or is it?
That was what Dan was talking about.
Luke talked about this.
Yeah, so I mean, I would say that just the periodic signals are not convincing at all, but I think the particular system, what's the phone number, Dan?
PG 1302.
Yeah, I mean, that seems like a very convincing
One of those candidates.
Yeah, where, I mean, you do, yeah.
So those are all selected, right, from, you study what you think the noise from an AGN should be, some kind of damp random correlated noise that we get empirically, and ask, given many, many realizations of noise, take Fourier transforms of all these light curves, and which of them have a peak that goes above this noise. So selecting whether you get a periodic signal, calling it AGN periodic or not, depends a lot on the characterization of AGN noise, which I think is still something that requires further work. But given the analysis done on what we think we know about AGN noise right now, there are 130 AGN out of 250,000 or so from the Catalina and PTF surveys that seem to have some type of sinusoidal period.
So that's my question, because I heard a talk maybe 6 months ago from Subi Gazari saying that they've done a similar analysis using data from pan-stars and have reanalyzed some of the claims of the things coming from Catalina and PTF, showing that they're consistent with just, red noise and not, essentially they're overinterpreted, given that that signal is maybe a cycle and a half or 2 cycles or something like that. Mm-hmm. And that, it essentially comes down to how you do your statistics, and they claim that none of those are convincing candidates.
Right, so I know there's been discussion recently too about PG 1302, where people with, I think Simon Vaughn, I forget where he is, wrote a paper, and I believe when they fit for the noise of, the noise parameters for the stamp random walk model for PG 1302, for example, they find different noise parameters. And if you get a different noise parameter, this red noise, or you have white noise and then a fall off, depending on where the peak in your signal is, whether it's in the white noise or the red noise region, which depends on its fit to the EGN noise, will give you a significant signal or not. So I think what's going on there is people are finding different fits to what the background noise should look like, so you get a different answer to whether your peak is significant or not. So I haven't kept up too much of that recently, but I think it's a really interesting question. This is why I've been working on different ways to corroborate that evidence rather than just the optical periodicity. What can we look at in other wavelengths, and what are the other pieces of evidence that can lead you to believe for or against this being
But Edo said most of them are just 1.5 cycles.
Mm-hmm.
Is that the correct description? Because I think I agree.
Yeah,
Red noise will produce things that will be 1.5 cycles very, very often, right? So Is that the way it is, that most of these candidates are just barely a cycle or a bit more?
Right, which you would also expect from a population synthesis, because you're going to find more with longer periods because they spend longer time there, so they'll be at the edge of the baseline. So right, if you make a cut where you say, for this to be selected, it has to have at least 1.5 cycles, then I think you're going to find most of 1.5 cycles.
Okay.
In that
What if you made a more aggressive cut? Say, I'm not going to believe anything unless I have four cycles.
Sure. I don't know how many of them
Nobody will
survive.
survive.
But if we wait,
The
if we wait
survey
10
baselines are
years,
just not long enough.
yeah.
Yeah.
So one thing to do is wait, right?
The other thing to do is what we've done, as Dan knows about with the DASH data, where 1302 is detected.
With a period.
Oh, well,
With
that's
the same
what's
period.
detected in your.
Yeah.
Yes, it's there.
You
And
have enough
that's 100
candidates
years
to
of
get
data.
actual
Dash
period?
goes back, so yeah, dash.
Yeah, DASH is our project scanning the plates here, 500,000 plates for time domain.
And that's a lot of cycles.
Well, it's 20 cycles.
Okay.
Now, you wouldn't detect it in each cycle individually, but you
Yeah.
know, folding the data, the full data set
Okay.
does show the effect.
So one real good candidate.
So if you looked
How
at
many
other
more?
ones,
4 cycles.
So
in a month.
PG1302 also has multi-wavelength.
No, I remember the story you have.
Yeah.
It's just beautiful, yeah.
But
Right.
still needs to wait.
Have you looked at other ones, Josh, besides that one?
We have, and as I was telling Dan the other day, there's some better analysis techniques that we're developing now that should improve the sensitivity. So that hasn't been done yet, but there's an obvious way to make things better.
Is it basically lone scarlet? Is that what you
It's-
guys are doing?
Yeah, it's one scarlet, but there are other, with any candidate period, one can do better by binning the data.
what about OJ287?
That was originally found with the Harvard plates, but it's there in the DASH data also, yes.
Right, I mean, that one is, what's interesting to me is that one is a very strange
Yeah.
system, right? And that's, I think, a pretty solid candidate in terms of the amount of data it has, in terms of something probably related to a binary going on in that system. But it's like a disk with an inclined companion.
Yeah,
touching
it's
the
an
disk.
extremely massive binary of 20 times 10 to the 10 solar masses with a mass ratio of 1 to 100 or something, where there's this disk around the big guy and the little guy is ripping through it. And it's not a periodic, it's actually not periodic
Yeah.
per se because the secondary is recessing due to relativistic.
This is a system that has been claimed to detect optical decay, right? The period.
I thought recently, yeah, there might have been something on
Oh,
there.
really?
Yeah.
Say because the period changed.
It's
That's
a lot of
right.
parameters.
I think we have time for one more question before, we're going to go to a format then when we have pizza and cake. Where is that going to be? We're going to have it in the ITC lounge so that we can continue the discussion. So let's have, well, I see 2 candidates for questions. Maybe they're compatible.
We'll have to wait longer to see if they keep their
3
hands up.
candidates. And you may be reporting on 4 candidates. Okay. James, we'll start with you and we'll see how fast it goes.
Yeah, I just had a very generic question. So when you look at LISA and LIGO sensitivity curves, there's 2 distinct bumps, right? They've chosen to go after things with a frequency of roughly hertz or 10 hertz for LIGO, and then much longer wavelengths for LISA. LISA, though, we have some freedom. We, in principle, could make the baseline a little bit shorter. I don't think it's actually been decided yet. And it seems like the current sensitivity curves are kind of picked to match where we think the black holes are. So I'm just curious if anyone on the panel thinks there's value to maybe trying to probe the mid-range in between LIGO and LISA better, and if that maybe would motivate a change to the LISA experiment to facilitate that.
So I heard Matt Evans talk about this at the BHI conference the other day. I don't remember exactly the technical aspect, but it's extremely difficult to probe that middle region. Yeah, because you can't do it from the ground.
Right.
And it's
I think
extremely
it's a
sensitive.
sensitivity limit.
Yeah.
So there's a sensitivity limit for what the space detectors can do. And then you gain by making the arm length as large as you can.
I see.
Yeah.
I see.
So if you try to go for shorter, you'll still be limited to that sensitivity limit of what a detector can detect, but your arm length is smaller, so you're losing. This is at least that's the way he described it.
Okay, quickly, we'll go to Josh.
I was going to come back to Edo's point about EM counterparts and the possibility that the Fermi event for the first GW detection is, I agree it's not at all statistically convincing, but it doesn't mean that there may not be something resembling a high energy, gamma ray burst like counterpart. And so the obvious thing to think about is how can one make both much more sensitive detectors in the few keV to few hundred keV energy range, which is, as of course we all know, is where GRBs are, but not that these are going to be GRB-like, but there may be similarities, and increase the coverage, the all-sky coverage and the precision. And there are ways of doing that, which I think are realistic in the next 10 years. But of course, another 2 sigma event, or better if it were 3 sigma, on the upcoming LIGO events would make this much more compelling. But I don't think we should rule it out. In fact, in Jan 11's very nice talk yesterday at the BHI conference, that opened another possibility for the pulsar black hole picture.
Yeah, I think the energetics there are very...
Which is pretty wild, but the energetics,
But
are
that
interesting.
model won't work for the double black hole, right?
Yes.
Unless you can
No,
14 gas
what we're
fields
going
into level.
The 15 Gauss.
16.
16 Gauss.
So it's only going to work for a
15
magnitude.
Something like that.
Okay, sure.
Yeah.
Okay, I'm going to refer to the leaders of the seminar. Should we cut it off now?
I think we should adjourn. Yeah.
Okay, well then, just before we do, I do want to take a moment to thank them both because I think they've done a wonderful job this semester. It was the other thing I did want to say is that we've really talked a lot about following up on this. There's so much interest and it's something new. We were hoping next year to start a group where we would come together, those of us who are interested, and review literature, talk about projects that we might have going on, and provide advice on those things where there are overlaps, to help move the research along. So we'll be in contact about that. And one thing I just want to say is, unfortunately, one of our group leaders is moving on to, well, I'll say fortunately, a faculty position. You want to say a word about that?
Oh, I hadn't prepared this at all. Just briefly.
And Dan has a hard time speaking. So.
Yeah, I accepted the position, tenure track position at the University. So I'll be starting there in the fall.
Excellent.
So I won't be here physically, but maybe virtually chiming in. I can join in.
I hope you will. I hope you will. Okay, well, I'm really pleased with the response here. We had more than twice as many people from the audience commenting. I was counting the commenting, asking questions, having creative ideas as we had on the panel. And we had a wonderful panel. So thank you to everyone sitting up here and to those of you sitting there.
Very good.
So I was Chair also reminded us, not 2 days.
Thank you for inviting me. I learned a lot. Oh, of course. I am 10 minutes away. I'm always happy to come here. I know. That's true. That is a possibility. That's why I will go upstairs. Yeah, this is nice.
Very.
Fortunately, I didn't have a part to it.
Yeah.
Something like that. Yeah. Fortunately, Edo had his arm sitting here to watch on. So I was
What about speed?
field? I guess it's sensitive to both bacteria.
More or less. There's some dependence on things like it's about sensitive.
So it may have happened.
Yeah, I mean, I don't even know the number of years we know, given some of the models.
It's substantially less sensitive.
So when they are establishing these spaces and other populations, are they trying to take care of that distribution or
That's, you know,
so that's going to give better localization?
Better localization.
I wanted to make a quick comment about selective publicity, and that is, when I looked at the LIGO, I looked to see if there was, I don't think there was a single CFA post.
Does help that.
Yeah, and because I looked. And now the issue, I guess, helping out CFA publicity is
Sorry guys, we need to take this.
So, but on the, so that's the negative. But on the good side, you guys are doing
There are all these different
unfortunately, going in the year or two, Edo's doing stuff, but then, they're not part of the fire. Maybe just look at that, overall, I mean, just having a series.
Certainly,
there's something, they're not exactly.
I guess actually the geology one way I can all that also.
Yeah, exactly. It's how far can you build a tunnel? Is there a town?
Rocks there and all that stuff.
When you guys are working with humans, that's right.
It's because these are.
Okay, one more question. Now, gravity waves, they do not thermalize. There's not enough time for them. Yeah, low cross-section I mean, even the insulated gravity waves are not reached Right.
Yeah, I mean, it's just funny that
there isn't a thermal. There isn't a more than the black thermal electromagnetic
I would be very surprised. I think we're doing well, but I think it's like somehow
yeah. I think it's to do with